Now that we know a little bit about lines and equation of lines, how to graph lines, etc., we can start talking about linear systems. Linear system. A linear system is two or more linear equations, that are considered at the same time. Two or more linear equations that are considered at the same time. So now instead of just considering one line, we're going to be dealing with two lines. To solve a linear equation, keep going with our notes here, to solve, underline, a linear system, is to find the point of intersection, which I will use POI, point of intersection. See that a lot, that acronym. To solve a linear system is to find the point of intersection of the two lines. So the systems that we'll be dealing with in Unit 1 are dealing with two lines, two linear equations, and they will intersect at some point. So it's important to know, earlier we said that coordinates x and y, a line is built off of those coordinates. A line is built off of a collection of x and y. This point has x and y, 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 and if we fill in all the gaps, we get a line. Y depends on x, so every time we have an x value, we get a y value, and it forms a line. Now, in a system of linear equations, where we have two lines, this line, this second line, also has all these coordinates x, y. And it just so happens that where they intersect at one point, if they intersect at one point, they're going to share the same coordinates at that point. So the coordinates, a certain coordinate xy is going to satisfy the equation for line 1 as well as the equation for line 2. And that's what we're doing when we're solving linear equations. Well, let's apply what we've just talked about with linear systems to a word problem. We're going to be translating this word problem into algebra using numbers and letters, values and variables, in order to solve this problem. So we have Ian. Ian owns a small airplane. He pays $50 an hour for flying time and $300 a month for hangar fees at the local airport. So there's one sentence that we're going to be translating into algebra. Carrying on. If Ian rented the same type of airplane at the local flying club, it would cost him, here comes our second, $100 per hour. How many hours will Ian have to fly each month so that the cost of renting will be the same as the cost of flying his own plane? So we've read the paragraph carefully, and we need to determine what things are unknown. What things are unknown? Well, we know how much he pays per hour for flying time. We know how much he pays for the hangar fees. And we know how much it would cost him to rent the plane. But we don't know the number of flying hours that Ian is going to fly each month, and we don't know the total cost of flying. So these are going to be our variables. Our variables are the unknowns in the situation. So we're going to translate the given sentences into two equations. Then we can graph the two equations to find out where they intersect, to find out how long he'll have to fly in order to save money by owning his own plane, or determining that he would be better off renting a plane. So let's do that. I've rewritten our two sentences that need to be translated into algebra so that we can have them in front of them while we talk about this. We've also determined that the unknowns in the situation is right here, our flying time, and in system number 1 and 2, what will be the total cost? Which option is going to be better? Well, we have to know the total cost of both options for the same amount of flying time in order to make that decision. So we're going to choose variables for our unknown. Since one of the unknowns is cost, we are going to let C, capital C, represent the total cost. And we have to mention that that is in dollars. Our other unknown is the number of flying hours, and we're going to measure that in time in hours. So let T represent the time flying in hours. And this is an incredibly important step in solving word problems using algebra. It's also one that we sometimes find very difficult. First of all, identifying the unknown information, and then coming up with a sentence for each, a let statement for each, that makes it very clear which variable, C and T, are going to be used and which units they're going to be measuring. And it's written out in a nice clear sentence that now I can use C and T in my algebra and my figuring out and my answering, and I'll understand the whole time what those variables stand for. So we have our two sentences that need to be translated. Let's go ahead and tackle them and get two sentences. So in the first sentence that we have, Ian pays $50 an hour for flying time and $300 a month. Well, T is time in hours. So Ian is paying 50T, and each month he's for sure going to pay $300 for renting some hangar space for parking his airplane. So equation 1 translates into the cost for 1 month in dollars is 50 times T, that's $50 for every hour that he's flying, plus, right up the top, $300. Equation 2 is a lot easier. The renting cost, total cost whenever Ian is renting, is going to be 100T. Now, both of these equations can be used to draw a line, and that's what we're going to do. But I'm just going to outline again. Here we have a line pretty much in slope y-intercept form. Same here, except the y-intercept is 0. So we can see that the rise over run here is 50 over 1, and the rise over run here is 100 over 1. So these lines do not have the same slope, which means they're going to intersect. Right at that point of intersection is where situation number 1 and situation number 2 cost the same amount. That's going to be the number of hours where it's the same cost. Anything in this region, one of the options is going to be better. In any amount of time in this range, the other option is going to be better. So our goal is to find out when it is better for him, or sorry, when will it be the same? How many hours will Ian have to fly each month so the cost of renting will be the same as the cost of flying his own plane? So again, finding the point of intersection of our linear equations, and we're going to do that by graphing the two lines on the same grid. Okay, I've gone ahead and written our two equations. I've got the cost of buying and owning your own plane in blue, the cost of renting the plane for Ian in green. I've gone ahead and drawn my graph that we're going to be filling in, and we're just going to plot both of these lines. We're going to plot both of these lines and find the point of intersection. Now both the equations are already in the form y equals mx plus b. So we can just use the y-intercept as a starting point and then use the slope to find the other points on the graph. So in this case, our y-intercept is 300. So I can make a point on the y-axis at 300, and the rise over run is 50. So I'm going to rise 50 for every hour that Ian is flying in his plane. So we're going to go over 1, up 50. So over 1, up 50. 350 is right in between 300 and 400. Over 1, up 50. over 1, up 50, over 1, up 50. Alright, we've got enough there to draw a good length of line here. You can see it's just going through the corners of each of my boxes anyway. So here is a line that represents situation 1, Ian owning his own plane. Alright. And I want to make sure I label that. I'm going to label it just out of the way here. We've got C equals 50t plus 300 in blue. And we'll move down to the cost of renting the plane. The Y-intercept is 0, and the rise over run is 100, so every hour he's going to go cost $100. 2 hours is $200, 3 hours is $300, 4 hours is $400, etc. And I now have enough information to draw a straight line through those points. I can label my green graph as C equals 100t, and I can find my point of intersection this way. My point of intersection is not perfect, but it's right there. It's where my two lines meet. That's where they have the same value. So they come to an intersection at the point on the horizontal axis 6, the vertical axis 600. So this is the point 6, 600. That means that after 6 hours of flying, option 1 and 2 will cost the same. And what is the cost? Well, the cost will be $600. And I can check to see that that solution is correct. So over here in equation 1, the cost equals 50 times t, which is now 6, plus 300. Cost after 6 hours for owning your own plane is 300 plus 300, which is 600. And in equation 2, the cost of renting your own plane after 6 hours is $600. So that is indeed the point of intersection. And now we need to write a conclusion to actually answer the problem. Remember, the problem was how many hours will Ian have to fly each month so that the cost of renting will be the same as the cost of flying his own plane. And so we write that in a sentence. If Ian flies 6 hours per month, comma, the cost of owning will equal, or will be equal to, will equal the cost of renting. And there we go. We've taken this big word problem, this whole paragraph of information, we've reduced it down to 2 algebraic sentences, we graphed them, found their point of intersection, interpreted their point of intersection. That means we've figured out what it means. 600 means that after 6 hours, both options will cost $600, after which owning will be a better deal, before which renting will be a better deal. So if he's planning to fly more than 6 hours per month, he should own his own plane. If he's only planning to fly between 3-4 hours a month, he's better off renting. And this kind of comparison is what makes linear systems so helpful. So for example, you could compare the cost of 2 options for owning a cell phone, and you could graph them in a linear system here, and you'd be able to determine what's the best option for you as far as owning the right cell phone and having the right cell phone plan. More on linear systems coming up. Now, example 1 gave us both of our equations for a line in the form y equals mx plus b. But sometimes they're not given in that form. Actually, quite often they're not given in that form. Sometimes it's easy to rearrange them into slope y-intercept form, y equals mx plus b. But other times you may wish to graph using intercepts, using a different method, like we talked about in the last video. So example 2 has us finding the point of intersection, and the equations for the 2 lines are x minus y equals -1 and 2x minus y equals 2. And we need to find the coordinates of the point of intersection. We're going to use method 1, which is graph using slope and y-intercept. That's the form y equals mx plus b. So we're going to rearrange both of these equations into the form y equals mx plus b, and what you notice about these two equations is that's not difficult to do, because the y variable is already isolated. It doesn't have a numerical value in front of it. So y is by itself, so all we need to do is step one, rearrange. So we'll take equation number 1, which is x minus y equals -1, and we need to rearrange it into the form y equals mx plus b. So what we're going to do is we're going to get, I'm going to move y to the other side because that's easier. I want to work with a positive y. So step 1, I'm going to add y to both sides. So in order to get rid of y over here, I need to add y. And in order to maintain equivalency, in order to make sure this statement remains true, I need to do the same thing to both sides. So here we now have x equals -1 plus y. Now to get y by itself, I'm going to add 1 to both sides. So now I have x plus 1 equals y. And so that we can see it more easily, I'll rearrange this just into y equals mx plus b, so it's easier for us to see y equals x plus 1. Good. Equation 2 is 2x minus y equals 2. You go ahead and give equation 2 a chance on your own. Rearrange it into the form y equals mx plus b. Okay, if you're ready, you can look up and check what we have here. Equation number 2 should be y equals 2x minus 2. Okay, I've set up my graph. You can go ahead and do the same. Remember, we have our x and y axes with arrows on the end. I've labeled a few points along the axes, 1 to 6 on the x and 1 to 5 on the positive y. We've got both of our equations for a linear system up there at the top. And now it's just a matter of graphing them. We can use our slope and our y-intercept to graph these guys. So here goes equation number 1. Y equals x plus 1. Y-intercept is 1. And slope is 1. 1 over 1. So every time I go over 1, I'm going up 1. That's an easy one to draw. And I want to make sure that I label this as y equals x plus 1. And I can draw my second graph, my second line here, which has a y-intercept of -2 and a slope of 2. So it's rise over run. 2 is the same as 2 over 1. So I'm going to rise 2 every time I run 1. So we're going up 2 over 1, up 2 over 1. Up 2 over 1. Ooh, and there's my point of intersection. I have enough points to draw my line. I want to label that line, y equals 2x minus 2, and identify my point of intersection. The point of intersection happens at x equals 3, and the coordinates of that point are 3 on the x-axis and 4 on the y value of the coordinate. Well, step 3 is simply to check that the point 3, 4 actually does lie on both lines. So in order to do that, we need to substitute x equals 3, y equals 4 into both of our original equations. So we'll take equation number 1 in its original form, which was x minus y equals -1. And our goal is to see if the left side of this equation truly does equal the right side of the equation when we sub in our coordinates. You can probably see that it does, but we're going to be talking about this left side and right side strategy for seeing if two statements are equivalent. So the left side in this case is x minus y, the right side is -1. So we need to work through this left side in order to see if it does equal the right side. So we're going to sub in the coordinates that we found, which was x value of 3, y value of -4, and that equals -1, so it checks out. Therefore, 3, 4 is a point on the line x minus y equals -1. It is on the first line. And we'll go ahead and check the second line here. We should write our last statement, left side equals right side. So here our original equation for the second line was 2x minus y equals 2. So the left side is 2x minus y. The right side equals 2. We'll sub in our values for our variables. X is 3 and y is 4. We'll work that through. That's 6 minus 4 equals 2. Therefore, the left side equals the right side, and we've determined that the point 3, 4 is on both lines, meets the requirements for being on both lines. It satisfies both equations. So the point 3, 4 lies on both lines. And then we write a conclusion. The coordinates of the point of intersection are 3, 4. So over here we could say the coordinates of the point of intersection are 3, 4. Done. I'm not going to show it here, but you could also have graphed these two lines by using their intercepts. So you could leave the equations in their given form, x minus y equals -1 and 2x minus y equals 2. Find out what the y-intercept and x-intercept is for line 1, graph it. Find out what the x-intercept and y-intercepts are for the second line, graph it. Find their point of intersection, and then double check the same way we've double checked here. Many strategies for solving many problems. In example 3, we're going to be tackling an internet problem. So there's two internet providers, and we want to decide, Brian and Catherine rather want to decide what internet access to get for their home. There are two companies in the area. IT Plus charges a flat rate of $25 per month for unlimited use. Techies Inc. charges $10 a month plus $1 per hour for use. If Brian and Catherine expect to use the internet for approximately 18 hours per month, which plan is the better option for them? So this time we're not just finding the point of intersection, we're using that information to find out, well, are they using it more than that, or are they using it less than that, and if so, which plan is more cost effective for Brian and Catherine? First, we need to represent each situation with an equation. Then we're going to graph it, see where the two lines intersect, find where the cost is the same. In order to graph these equations, in order to graph these situations, we need to have two equations. So we need to introduce our variables. Step 1, introduce our variables. Again, we're talking with time, so we're going to let t represent the number of hours of internet use. Let t represent the number of hours of use. And we're going to let C, capital C, represent the total cost, the total monthly cost. Alright, we've got our two equations. Let's go ahead, our two variables. Let's go ahead and write our two equations for IT, capital IT plus. The cost is a flat rate of $25 per month. So IT plus cost equals $25. No more, no less. For techies, the cost is a $10 flat rate plus $1 per hour. So 1T. Alright, time to graph our two equations. So for IT Plus, that's pretty easy. It's going to be $25 all the time, whether I use it 1 hour, 2 hours, 3 hours, 10 hours, 20 hours, 50 hours. Hopefully I'm not on my computer on the internet 50 hours a week, but or a month, sorry. That line represents the cost of going with IT Plus, so C equals 25. My next line is for techies. C is 10 plus 1T, so no matter what, at 0 hours, a flat rate of $10, and then every hour is another $10. So if I go over 10 hours, I should be going up $10. If I go over another 10 hours, I should be going up another $10. And I can draw my line for techies. Don't need to worry about anything over here on the left side of the y-axis because, well, I can't pay negative money and I can't spend negative hours on the internet. So we're only dealing with the quadrant 1 here, positive x-axis and positive y-axis. And we can see here our point of intersection happens at 15 hours. So the point of intersection here, is 15.25. So after 15 hours, the cost of both plans is $25, but we've been told that Brian and Catherine are going to use the internet for approximately 18 hours per month, which means they're over here, 10, 15, about here. So which plan is cheaper if they're using it for 18 hours? That's going to be the constant rate of $25 a month from IT Plus. It's going to be cheaper in the 18. So the two plans cost the same for 15 hours of internet use. The cost is $25. For more than 15 hours, the cost of techies goes up. It's going to be more than $25. But the cost of IT Plus stays at $25. So if Brian and Catherine expect to use the internet for 18 hours a month, they should choose IT Plus. We'll write that in a quick sentence. If Brian and Catherine intend to use internet 18 hours per month, IT Plus is the better deal. Now you've got enough examples here to get started on some of your homework. Give it a shot, and we will talk about it in class tomorrow as well.